Okay, let's go ahead and get started. Uh, as promised, I'm just going to answer your questions. So, what questions do you have? What sorts of things are you worried about that brings you away from Netflix this evening? Yes, just a second. Let me get closer here.
Problem number one, letter A.
Oh, yes, certainly. So that's in the other exam. Okay. Okay. That's just not helpful. That one there. Is that the one?
The first one. The first one.
The first problem?
Yeah, first problem.
Oh, that one there? Okay. Uh, certainly. The first thing that you want to do with a problem like that is you would like to decide which branches are independent of each other. And if I uh, look at this circuit, you see that this combination of A, B, C, and D have their own connections to the battery. Okay, so these are going to be independent. And then all of the rest of this is independent. So what you want to do is draw those two branches the same. I thought that I brought down a bunch of pens, but this one here, that's no good either. Okay. I will be right back with some pens.
I have some.
This is unfortunate.
Okay. That's enough. She's too far gone. I go upstairs.
Okay, I'm sorry, that was my fault. Uh, so the simplest one of those branches is just A, B, C, D, like that. Now, we'll call that branch one. I want to call branch two that. Exactly the same. Now I just need to figure out which bulbs are these bulbs. Well, it looks like I've got two indicator bulbs. Everything in branch one has to go through A and D. Everything through branch two has to go through E and J. And so this is going to be bulb E, and this is going to be bulb J. And then I ask myself, if Fred goes through E and J, how can he get from one side of the battery to the other side of the battery with only going through one other bulb? I hear Fred goes through A and D, and he just has to go through one other bulb, either B or C, not both. So it looks like F and G are the bulbs I'm looking for. Well, again, if this were the circuit, you'd be really, really happy because that's very, very easy. So I asked myself what's missing, and what's missing are these two bulbs over here, H and I. And you can tell that this is an old exam because I don't use the letter I anymore, because capital I we often use for current, and that's just confusing. So I always skip from H to J, but this is an old uh, exam question. So because I've added this new path in parallel, that means whatever resistance I had here, I've got less resistance here. I've got a new opportunity for flow. So when the current splits here, I'm going to get more than half going that way and less than half going this way. Okay. Now the first uh, comparison that I'm asked to make is A and J. A versus J. Well, since A gets all of the small pizza and J gets all of the large pizza, J is going to be brighter than A. If I compare B to F, B versus F, B is getting exactly half of the small pizza. F is getting a little bit more than a third of the large pizza. That's a pizza problem. I can't solve that with current. So I'm going to switch over to voltage, and I will pick a path that goes through B from one side of the battery to the other, and another path through F from one side of the battery to the other. And so that's going to give me A plus B plus D is equal to, I'm going to call this the red path over here, E plus F plus J. Now, are any of these voltages the same? How would you compare the brightness of bulb A to the brightness of bulb D? Yeah, they're in series. Everything that goes through A has to go through J. Likewise, everything that goes through E has to go through J. So these two are the same brightness and these two are the same brightness. So I can rewrite this as 2VA plus VB is equal to 2VJ plus VF. Everyone see what I did there? Okay. Well, now, if I'm trying to compare these two, I first of all have to compare these two. Well, if I'm looking at 2VA and 2VJ, I already know that J is brighter than A. And so twice the voltage of J is going to be bigger than twice the voltage of A. Red team wins. So now let's compare the other two. Be careful to keep them on the correct side of the equal sign. If the red team won this one and it's overall a tie, the blue team has to win that one. And so I know that B is going to be brighter than F. Well, C and H, I know that C is the same as B, and we just said that B was brighter than F, and I know that F is brighter than H. Okay, I lost track of what I was trying to compare. C versus H, I know that C is brighter. And the reasoning, I can just say, well, C is equal to B. We just said that that was brighter than F, and F is brighter than H. Does everyone see why C is brighter than H? When Fred gets here, he's got a choice. He can either go through a single bulb on this path, or a single bulb on that path, or a difficult path with two bulbs here. And so these guys are going to get the same amount of current, and this one's going to get less current. Current favors the path of least resistance. And so C is going to be brighter than H. The next one, D and G.
Professor Francis,
Yes.
sometimes I think that when we add another path, that red pathway, that's gonna decrease resistance and increase current. And so I would initially think that that H would have more current than B because it's the path of less resistance. There's more options for the current to pick.
Yeah, and you didn't finish your sentences just then.
Okay.
When I've got more paths, I increase the current where?
In the
In the battery.
in the battery.
In the battery, yeah. Yeah, just increasing paths doesn't necessarily increase current there. It increases it in the battery. Yeah. We have to be careful with our language with that. So certainly the extra path there has increased the current through that branch, but not necessarily through this extra path. Indeed, if that extra path had 27 bulbs in series, it would still increase the current through the battery, and it would give me more current in branch 2 than branch 1, but hardly anything's going to trickle through that extra path with 27 bulbs. Okay. Okay, the next ones are D and G. D and G. Okay, so this one here and this one here. Well, again, I already know that B is greater than F, which is equal to G. So I know that B is greater than G. How does D compare to B?
Bigger.
Which is brighter, D or B? D, yeah. B only gets half the current through D. And folks, just as a rule of thumb, whenever you're comparing an indicator bulb from one branch to a bulb that's not an indicator in another branch, your gut's telling you the indicator bulb is going to win. And sure enough, B only gets half of the current through D, and it's going to already be brighter than G. So I know that D is brighter than G. Well, now in this problem, we make a change. Whoops, my bad. What I do is I short out bulb H, attach a connecting wire to both sides of H. Well, let's do that. And it's asking us about some of these bulbs. The first bulb it asks us about is bulb C. So bulb C is on an independent branch parallel across the battery. So C will not change. Now, to be clear, I've added a new path. The current through the battery will increase, but this path is independent of that path, so this current stays the same. What happens is that the current in branch 2 gets bigger. And that means that E and J are going to get brighter. Well, what's that going to do to F and J? I'm sorry, F and G. Well, let's do this in order. J is going to become brighter, and that's because it's an indicator bulb for that branch, and that branch just got more current. So E and J are both going to get brighter. But bulb G, it's now getting a smaller share of more total current. Remember, this used to be the cluttered path. This used to be the one that got less than the other two. But by shorting out H, this branch only has one bulb on it anymore. And so it becomes equal with these two. So G used to get more than a third, and now it gets exactly a third. Its share went down, but the current through the branch that it was sharing went up. So this is a pizza problem. So if I take a path through G and say the voltage across E plus the voltage across G plus the voltage across J has to add up to the 12 volts of the battery. Well, I know that E gets brighter because it's an indicator bulb, and J gets brighter, it's an indicator bulb, and if it's still got to add up to 12. So G has to get dimmer. Has to get dimmer. Okay. And finally, bulb I was getting less than a third of the current through branch one, and now it's getting exactly a third of the current through branch. I said that wrong. Let me start over. I used to be getting less than a third of the current through branch two, and now it's getting exactly one third of the current through branch two. Its share of the current through branch two went up, and the current through branch two also went up. So it's getting a bigger share of more current.
Can you explain again why branch two's current went up when you shorted that out?
Oh, there's 4 ways to change a circuit. I can add a path, I can remove a path, I can clutter an existing path or declutter a path. By shorting out bulb H, I like to think of it as adding a new path, a really good path, a path with no resistance on it. Some people like to think of this as decluttering a path by taking that bulb out. Either of those changes is going to make it easier for current to flow. And either of those changes is going to make the current through the battery go up. Now, because branch one is independent, none of that increase here is going to be felt in this branch. It all has to be felt in the branch where I made the change. Does that answer your question?
How did you know to use the voltage model instead of the current model?
For which?
For this one, you use the voltage model instead of the current?
Oh, you mean here?
Yeah.
I tried to use the current model and I got pizza. And that's the way you always know. At least that's the way I like to do it. I always start with the current model. I be the river. I see if that works. If it doesn't, if it gives me a pizza problem, I switch over to voltage. In this case,
Like what told you to use the voltage instead of what told you to switch?
oh, well, there were 2 changes going on for bulb G. Its share of the current through branch two was going down from more than a third to just a third. But the current through branch two was going up. One of those is trying to make it brighter. One of those is trying to make it dimmer. And our model doesn't tell us which is going to win out because our model doesn't give us any numbers. It just says more or less. Does that answer your
Yeah.
question?
How did you figure out that there was more current going through the entirety of branch two?
Branch two, because I was adding a path, and adding a path makes it easier for current to flow. Whenever you add a path, no matter what's on that path, it can have 5 bulbs, 50 bulbs, a dead bloody fish, don't matter. Anytime you add a new path, that increases the flow through that branch.
And is that only if they're parallel to each other?
No, that's always, always, always for every circuit. Anytime I add a path, now be careful, you have to finish the sentence. This gentleman got in trouble with this. Whenever I add a path anywhere in the circuit, I always increase the current through the battery, just through the battery. And then you've got to be the river and see where does that extra current go? And because branch one is independent of branch two, they're parallel across the battery. I can't change any of these bulbs' brightness. So if the current through the battery went up, the current through branch two's got to go up. Yes, sir.
So there's only 2 branches right now, really.
I'm sorry.
There's only 2 branches right now.
Oh, only 2 branches instead of 3? In order for a branch to be independent, it has to have its own connections to both sides of the battery with nothing but wire. And if I look at the those are all bad. These are the good ones. Okay. If I look at these bulbs, I've got a connection on this side of the battery with nothing but wire, and a connection on this side with nothing but wire. If I look at this branch, I've got a connection on this side with nothing but wire, and a connection on this side with nothing but wire. But if I try to do the same thing with this, I run into bulbs on both sides. Okay.
You might have already gone over this, but could you please clarify how increasing the current of the battery will affect, this, circuit? If there's two, explain how increasing the current affects when it's right now, when the H has been taken out versus when it's normal, if that makes sense. I don't know if I said that well.
So, you mean before I short that bulb, or
Yeah, with H shorted, if we increase the current, and then when H has not been shorted.
say it.
With how it increases, how we increasing the current of the battery, how does that impact the system with H being shorted and then H not being shorted?
So it goes back to the question of do you believe that adding a new path that didn't exist before makes it easier for current to flow? In other words, if we were racing for the doors to get out of this room, and suddenly a trap door opened in the ceiling and a rope fell down, would that make it easier to get out of the room or harder to get out of the room? Well, not everyone could climb that rope, but he could. And if he's going up the rope, he's not fighting us at the door. So any new path is going to make it easier to get out. Okay. Now, when I look at the resistance formula for adding a new path, 1 over R equivalent is equal to 1 over R1 plus 1 over R2. If I add a new path in parallel, it's like adding a new term right there. And if you go through the math, anything I add over here is going to make the right-hand side of this equation bigger. But that's 1 over R equivalent. Anytime this gets bigger, R equivalent gets smaller. Okay, because it's 1 over in that equation. So I think if that math isn't speaking to you, just remember that if you think of Fred's trying to get from one side of the battery to the other. If you give him a new lane on the freeway, that's making it easier for the flow. If you give him a new obstacle that didn't exist before on the same path he was going on before, that just slows him down. That lowers the current through the battery. That help?
So when you add a path, you are decreasing resistance and increasing current through the battery. But that does
Decreasing resistance.
Yes.
And increasing current through the battery. Yes.
Does that increased current only go to the second branch or where that was added?
Yes, because the primary rule, the rule above all others, is that parallel branches across the battery are independent. And we saw that in class, that I could hit bulb G with a hammer, smash it to smithereens. A, B, C, and D don't care. I could unscrew B and leave the empty socket behind. E, F, G, H, I, and J don't care. And the reason for that is that if they have their own connections to both sides of the battery with nothing but wire, I've got 12 volts from here to here, regardless of what I do to this branch. Likewise, I have 12 volts from here to here, regardless of what I do to that branch. The push, the pressure difference is going to be the same on each branch, regardless of any changes to the other branch.
Okay, so I understand what you're saying, but if we were to like add an indicator bulb before branch 1,
Yes,
that would make them not independent.
exactly. Everything.
Why?
Why?
Yeah.
Because if I put an indicator bulb here and I short this out, I have increased the current through the battery, right? And that's going to make this indicator bulb brighter, and that's going to change the voltage that's left over for this branch. So it's no longer independent. A change over here suddenly changed the voltage across the other branch. Okay. Yes.
Can you explain voltage going through parallel branches versus through like bulbs in a series?
Oh, well, first of all, I just need you to wash your mouth out with soap. Because you were talking about voltage through, and voltage doesn't go through
The
anything.
change in voltage between.
Across. If there's basically three types of relationships you've got. You've got parallel across the battery. You've just got regular parallel. And then you've got series. Anytime they are in parallel, whether it's regular parallel or parallel across the battery, the voltage across A has to equal the voltage across B. It's like coming down the mountain. If you're coming from the same starting point and the same ending point, you're going to come down the same number of elevation, the same meters. In this case, the voltage across, if this is a 12-volt battery, the voltage across A would be 12 volts, the voltage across B would be 12 volts. Over here, if this is a 12-volt battery, the voltage across A would be something less than 12 volts and something less than 12 volts, but it'd be the same, okay? And so if I look at V equals IR, if the V is the same, and one of these has a bigger R, it's going to have a smaller I. So let's say that A has the bigger R and B has a smaller R. That's going to give me a trickle of current here and a gusher there by V equals IR. And the same thing is true here. If if A is the big resistance and B is the small resistance, the current is what's going to divide up with a trickle going the hard way and a gusher going the easy way. Current favors the path of least resistance. But here in series, it doesn't matter that A has a big resistance and B has a little resistance. I've got to have the same current through A and B. Not the same voltage now, but the same current. Because once Fred goes through A, he has to keep going through B. So that means that whatever I have is the same. So if I look at V equals IR, now it's the I that's the same. And so if I've got a bigger R, I'm going to have a bigger V. And that's, remember, the battery just trying to get those coulombs through the boxes that are in series. I've got to get the same number of coulombs through box A and box B every second that goes by. And so that means if A is harder to get through, I'm going to use more of the oomph of the battery pushing coulombs through box A than box B. Okay. So here in parallel, the box with the bigger R is going to get the smaller current, but they have the same voltage. Here, the box with the bigger R is going to get the bigger voltage, but they have the same current. Okay.
And then how do you find in that middle one what the voltage is of C?
Oh, the voltage, you would have to look at things that are in series, and C is in series with this parallel combination of A and B. And so I would have to compare the resistances of those two boxes. And that's, remember, the most important tool in your toolbox, being able to look at two boxes and say, oh, that box up there has 4 times as much resistance as the box down at the bottom. And then you can say, oh, it's got to have 4 times the voltage across it that the bottom box has. Now you can't make that determination with bulbs. You've got to do it with resistors. But with bulbs, you can just say more or less. This box has more resistance. This box has less resistance. And so in those cases, if I've got a 12-volt battery, I can say, oh, I've got more than 6 volts here or less than 6 volts there. I can just, and with situations like this, I know that if I have 3 bulbs in series and it's a 12-volt battery, this would be 4 volts, 4 volts, and 4 volts, right? But I don't have 3 bulbs in series. I mean, A and D are in series, but A and D are brighter than B. And so when I divide up the 4 volts, I'm sorry, the 12 volts, what I'm going to get with this extra branch, I'm going to get greater than 4 volts, greater than 4 volts, and less than 4 volts. Because these two have a bigger share of the total resistance than that. And so they get a bigger share of the 12 volts. Okay.
In that example you just did, what if there was more than one bulb on the path of B and C? Would that still be the case?
Let's say there were 27.
What if there's 27 on both of them?
Oh, no. if there's 27 just on one, then I know that this has less resistance than a single bulb. But if there's 27 on both of them, that's way different. You have to be able to say, this is exactly the same as that, except, and you write except in capital letters, and that except is what you circle in red. And you don't care what it is, just how it's added. Okay. And know this, that I will, on an exam, always when you're comparing two networks, I will make it so that you can circle just one thing. Okay. And so if you find yourself saying, oh, well, when I went from branch one to branch two, I added this new path in parallel, but I also added this new clutter in an existing path at the same time. You're looking at it wrong. You've got the wrong bulbs identified as your indicator bulbs.
I have a question about how the voltage rearranges itself across like bulbs when you're opening switches or removing bulbs, especially like when they're in parallel.
Well, I think we can all agree that the battery has no eyeballs,
Right.
okay, and can't look down the path and say, oh, this is coming up. The battery just pushes, okay? Just like when I blow on a straw, I just push for all I'm worth, okay? With all my old age, okay? And as you open switches or unscrew bulbs or change the circuit, you're just making it easier for the flow, but the battery just keeps pushing like it always has. And the result changes because you made one path easier by making your change or one path harder by making your change. Does that answer?
So, like for example, if you took out bulb A, it wouldn't affect the voltage across.
Take out bulb A?
Yeah, it wouldn't affect the voltage across B, right?
If I take out bulb A, it changes the voltage across B huge. Am I talking about the same?
Branch two.
Yeah.
Are you talking about this circuit here?
Nope.
No. So which, you're talking about these over here?
Yes.
Oh, yeah. If I remove that, I suddenly have changed the resistance of this box. And so that's going to change B and it's going to change C. But if I remove this, I've still got 12 volts across here. That's what independent means. I can completely take that branch away. The only thing I can't do is short out that branch because then I short out the battery and I destroy the whole shoot match. Everything goes dark. Then the independence is destroyed with the battery and the extra wire melts. We won't do that.
I have a specific example. Can we go over the last problem on the tutorial where we remove this bulb?
Okay.
Brighter.
So like we did in class today?
I don't remember doing this specifically in class today, but
So
oh, yes.
so is that the
Yes,
same circuit? So by taking out that bulb and leaving the empty socket behind, now this box looks exactly, the way the camera's set up, I'm only recording this screen over here, so I'm gonna have to. So by taking out that bow, this box now looks the same as the bottom box. And so what I care about is not the resistance of the box as an absolute number, but what share of the total resistance that box represents. And so by going by increasing the resistance of that top box, its share of the total went up, and the bottom boxes and the middle boxes, their share of the total went down. And so that tells me that 6 is going to get dimmer, 4 and 5 are going to get dimmer, 3 is going to get brighter, 2 is going to be out. It's on an incomplete path. Now, if I use the current model, I get the same answer. I've removed a path, the current through the battery goes down. 6 gets all the current through the battery. If the current through the battery goes down, it gets dimmer. Well, 4 and 5 each get exactly half of the current through the battery. If the battery current goes down, they get dimmer. But with 3, there's 2 changes going on. Its share went from more than half to all, 100%. And the current through the battery that it's sharing or was sharing went down. So it's getting a bigger share of less current through the battery. So that's where I have to go to the voltage model. The current model will not tell me what happened to 3, but the voltage model tells me right away.
Can we switch to a different question, or do you want to stay on this one for?
Are we, everyone's good? Okay, different question.
We do number 4, the one that you were showing in the beginning.
Oh, yeah. Boy, you just want to pray that you got one of these on your exam, because they are the easiest. This is where I want to be. It'll be down here. Okay. Now, all the ones that have the same shape have the same resistance. And again, I've told you this many times, I'm an old man with sad stories to tell. I've watched over many, many years as students have just bombed this question, this type of question, because they say, oh, well, I've got a square there, and it's got 1 amp going through it. So all the squares got 1 amp going through it. I've got a triangle there that has 2 amps going through it. So all the triangles have 2 amps going through it. No. Just because they have the same resistance doesn't mean they have the same current going through them. What matters is what percentage of the total resistance in that branch do they represent? And if that triangle is, I'm making this up, let's say that's 5 ohms. Well, 5 ohms in a circuit with 100 ohms is no big thing. But 5 ohms in another circuit that's only got 4 ohms with it, it's a big thing, and so those are going to have different amounts of current going through them. And so what you want to do is be the river. These questions are all about being the river. So let me just put this up here. So let me just really quick draw this, cause I can't draw on my computer there. So I've got a circle and two triangles. And over here, I've got a triangle. And then I come down to two, are those hexagons? I never learned all the names of the. Okay. And then over here, I've got a triangle and a square. And then it comes down and we have a square and a triangle. Okay. Now what I know is that I've got 1 amp here. I've got 1.5 amps there. And I have 2 amps here. And I've got 10 amps through the battery. Well, B the river. The river comes around with 10 amps and 2 breaks off this way, leaving 8 amps there. Does that make sense? Now, I know that these two are equal to each other and they're parallel to each other. And so when the current splits right here, whatever comes down that path, when it splits right there, it splits 50-50. So I must have 1.5 amps going through this hexagon, just like that one. And that means I've got 3 amps going down this path. Well, if 8 came into this node and 3 went this way, then that leaves 5 going that way. And when that 5 got here, one of them went that way. And so that means I've got 4 amps there. They come back together. I've got 5 amps again. But I know that a triangle and a square are going to split the current with 4 going to the, with 4 times as much going to the triangle as the square. So I'm going to get 4 amps there and 1 amp there. And then these are going to come together and that's going to be 5 amps. And then these are going to have 3 amps. They're going to come together with the 5 amps to give me 8 amps. And then these are going to have 2 amps. They're going to come together with the 8 to give me 10. And that 10 is going to go around.
So if the triangles have 4 amps on the third branch, wouldn't that mean that they also have 4 amps on the first branch?
Absolutely not.
Why?
So let's put some numbers in it. Would you expect these two ohm resistors to have the same current going through them?
Yes.
If you see this branch here, it's got 5,002 ohms in it. I'm just going to get a trickle. Whereas here I've only got 4 ohms there. I'm going to get a gusher.
Gotcha.
What matters is what it's in series with. Just because it's the same resistance doesn't mean it's the same current. Yeah. And that's what I was saying is that that's the mistake that lost people a lot of points when we have these types of problems. When and you know, I hate to admit this, and I'm probably gonna burn somewhere forever, but it's a multiple choice test. And I know that a lot of people make that mistake. And so that's going to be one of the answers. right? That's gonna be a trap. It's a trap. Okay, so don't fall into the trap.
Can we do 2A on this exam?
On this exam, most certainly. Oh, I am gonna work that problem in all its gory detail on Thursday, but I'll do it right now too. Then you'll just be bored on Thursday. You can just sleep during that. But let's look at that problem. No. Oh, got some. Can you read that? That's okay. We're asked to fill in the voltages across these bulbs A, B, and C for different lengths of nichrome wire in that circuit. And nichrome wire, you'll remember from tutorial 6, nichrome wire is a resistor. Okay, connecting wires we assume are perfect and have no resistance whatsoever. But nichrome has resistance, and the longer the nichrome, the more the resistance. And so what I know is that bulb B is parallel across the battery, and so the voltage across bulb B has to stay 1.5 volts. Well, what else do I know? Well, I know the voltage across the nichrome, and I know that the voltage across the nichrome is equal to the voltage across bulb C. And I say voltage, but I mean voltage difference. How do I know that? Why do I know that?
They're parallel.
Anyone? Say it.
Just like Parker said, because they're parallel.
They're parallel, yeah. Any parallel path has to have the same voltage across it. And so I know that if there's a half volt across the nichrome, there's a half volt across bulb C. And if there's a 0.6 volts across the nichrome, there's 0.6 volts across bulb C. And this would be 0.64, and this would be 0.67. Well, now how do I figure out the voltage across bulb A? Well, any path from one side of the battery to the other has to have a voltage drop equal to the battery voltage. And so that means that the voltage across the nichrome plus the voltage across bulb A has to add up to 1.5 volts of the battery. And so if the nichrome has a half volt, bulb A has 1 volt. If the nichrome has 0.6 volts, bulb A has 0.9 volts. And if the nichrome has 0.64, this is going to be 0.86. And if the nichrome has 0.67, this is going to be 0.83. Does that make sense? Yes.
If then you have nichrome wire on one side. And you have a bulb C and nichrome wire on either side. Why would you add, you don't add 0.5 and 0.5 together, then subtract?
No.
Why?
Because Fred can only go down one of those paths Fred can either go through the nichrome or he can go through bulb C, but not both. And so any path that Fred goes down from one side of the battery to the other has to have the drop of the battery. So it's either A plus the nichrome or A plus C. Okay. Okay. Any other questions before we call it a night? I walked the dogs and fed them, so they're fine. My wife took the train up to Farmington to watch our grandson. He's in a color guard performance, and that's part of being grandparents is that whenever they have a concert, we get on the front runner and go and watch it. We sometimes we're just spending more time on that front runner than we care to think about. But they're moving to Missouri, so we're gonna wish that we could go on the front runner because it doesn't go to Missouri. Okay, I am going to post a review session from last year, and then we're going to review in class on Thursday, and hopefully, as we review and as we practice and we work more problems, it'll just start to feel comfortable. You're going to know before you go into that exam whether you've got a model that works. You know, you're going to start making predictions that come true, and then that will build your confidence, and you'll know that that you're ready. Okay, and if you're still kind of scratching your head, it's that, well, I thought that was going to get brighter and it got dimmer. You need to keep practicing. Keep practicing. Okay. Okay. Let's go home.
Either